Okay. So if somebody grows and gives me, and we can test it. Okay. So whatever. Or I think I'm supposed to come in after maybe 6 months one more time. So maybe at that time, if you are prepared with some sample, we can also test it more. Okay.
Sometimes protein makes some kind of crystals when you store it.
So coming back to this, so here is just, this is the diffractometer area, right? So how does it work actually? You can see here, it's a schematic diagram. So this is the crystal. We rotate the crystal 360 degrees. This is one of the angle, which is called phi. And this is the green one, is called kappa. It rotates the crystal in another direction. And then you have an omega, which is the blue, so which rotates the crystal in the third direction. And then you will actually move the detector for low resolution data and then high resolution data, like you can do like this. So there are a few movements because you want to collect as many diffraction spots as possible to arrive at the three-dimensional structures. Okay, that is the purpose of rotating all these angles to shine your crystal with X-ray in all parts of your crystal. Okay. So, yeah. So on the left hand side, you can see the diffraction pattern, and the right hand side, they are the structure, how they are established. Okay. So if you have a poor resolution, you can only see electron density. You will not be able to solve the structure. That is the issue with protein crystallography. In protein crystal, you will not be able to do it like small molecular people. Small molecular crystals are very good diffracting. So you can achieve a resolution up to 0.84. When you have a resolution, you see, higher resolution, your atom positions get clear and then you can establish the structure like this. But if you just have poor resolution, you can see just as a skeleton. So in protein, getting a resolution up to 1.4 angstrom is already difficult. Okay, so that is why what you do, you try to get as best crystal as possible to attain high resolution. Similar in small molecular crystal. If there is a crystal which is not giving a high resolution data, so then again you will not be able to solve it. But chances are less in comparison to the proteins. Okay. So then obvious question, can I do single crystal diffraction with my sample? How to do it? Okay. So then this is the typical view of single crystal. It can be different color, it can be different shapes, it can kind of looks like sometime and kind of agglomerates. Okay. But if you look at this, one thing you can clearly see, what is crystal, which is I already told, they have definite shape. It can be needle, it can be plate, it can be block, it can be trapezoid, whatever the shape. It has a definite shape and it has a definite size. Okay, this is all looking under microscope. It can be very, very thin needles. It can be plates and different colors. It can be, you see, with this kind of agglomeration, but you can see some of the crystals here. So you can get nice crystals like that. It depends, like it's about your sample. So you can do all these things. Then what is required? Ideally, it has to be a single crystal. Sometimes even couple of crystals, 3-4 crystals also you can solve, okay, with the help of the software. And then the what should be the dimension of your crystal? You can go anything below 500 micron. If it is bigger, what you do? You can cut. Okay, but if it is smaller, you cannot grow bigger, right? But if it is bigger, you can cut. So anything below 500 micron, and you can see my colleague limit is 4 micron crystal. My limit is around 10 micron. Okay, my colleague went till up to 4 micron crystal because you need a high resolution microscope to see a 4 micron crystal. It is not easy to see a 4 micron crystal. Okay, so you can really do with this instrument, and then it requires manual check and manipulation under the light microscope. So that's what you have here, microscope. When you look under the microscope, the crystals are clear, generally sparky, nice regular shape, faces and edges. And you have a polarizing microscope here. When you rotate your polarizer, it should extinguish the light. Okay, so that means the light has to pass through once, and one time it should come. So that is the property of a single crystal. But glass won't show that. Okay, so then Okay. So these are the tools generally is required for a single crystal diffractometer. You need a microscope to mount your crystal, different kinds of needles to handle your crystals, and you have a goniometer and then goniometer bases to put your crystals, and oils for sticking your crystal. How do we actually do in our lab? Okay, so this is if you like, come 1 or 2 people in the next 2 days, we will be doing time and now again, and you can have literally look, but you can also look the video. So this is under the microscope what we are seeing here. So here my colleague is like really lucky, he has plenty of crystals, but generally you don't have, you have already seen, they have only few crystals you will get, and out of this you would like to select some candidates as for the diffraction experiment. Okay, so what he is trying to do is with the needle, he is trying to keep some crystals on the glass slide, one side of the glass slide. This may be an ideal candidate for diffraction experiment. Okay, so once he puts those stuff, then what he do, next step, he will put a drop of paraton oil or an NVH oil which is supplied with the diffractometer. Why this oil is used? You see, he put the drop of oil. So this oil is actually will not dissolve your crystals. One. Second is it is viscous. It will stick your crystal to the loop. Third is it will allow you to clean your crystal. Like it can remove any precipitate sitting or any secondary crystal. You can wash your crystal with this oil, and then it will allow not to react your crystal with the atmosphere here. So all these advantages will be gained by this oil, which is an NVH oil or a paraton oil. So now you could see that whatever the selected candidates, my colleague has moved that into the drop of oil, and then he tried to clean that. Once he cleaned that, he wanted to test under the microscope, this is a single crystal or not. Okay, so you can see in this video that he will rotate the polarizer and then want to see that whether it extinguishes. Let's concentrate 3 at the center, 2 at the bottom, 1 at the top. They are transparent now. These are looking dark. But when you rotate, these are getting transparent and the other 3 are getting dark. Right? So this is what the single crystal looks like. It should extinguish the flame polarized light. You can see again. Center 3 and the 2 at the bottom, 1 at the top. Right? So that's the property of a single crystal under the microscope. So now he is sure that these are all crystals and they are good, and now he wants to stick this crystal onto the loop with different sizes which is already available, and then put it onto the diffractometer. How we stick actually? These are all supplied with the instrument with different sizes of loop. They are made up of with nylons, okay, and it is put on the already crystal cap which are ready to use. So you just have to use it. So how to use it? Use them is just take that loop, you can see, and you want to take the crystal out of the oil, because the idea is to mount a crystal with as less amount of oil as possible. You could see, that's it. That one you are going to take it and putting onto the diffractometer. Okay, so, and here is another example. You can see now, this is also looked under the microscope, how we actually stick the crystal. This is in the oil again. We are trying to see which crystal is better. So there are big crystals, but we don't want to take big crystal. We want to take an ideal size crystal. Okay, so it's taking that crystal and trying to push it out of the oil, because you want to mount with as less amount of oil as possible. See? Okay, so now he takes the loop. Yes, the loop is there. So now he is going to just scoop it, nothing else. Yes, it's it. That's it. We are going to take this onto the diffractometer. So then you put the crystal on the diffractometer, and here this is the center of your diffractometer. So X-ray is coming in this region. X-ray is not coming everywhere. X-ray is coming only in this region. So you want to center your crystal. So once you center your crystal, okay, so you can see different size and different shapes of crystal which we have mounted here, right? So you can basically center this. Just some videos, you see they are out of center at the moment, and you are going to center it. See, like that. You move manually, or if you have a motorized goniometer head, it can do motorized way as well. You don't have it here, so you have manually. You have to do. You will put it to the center like that. Once you put those crystals in the center, so then you shine the X-ray for a few minutes or for a few seconds, maybe 1 second, maybe 5 seconds, maybe 10 seconds, depending on the scattering power of your crystal. And if you see bright, round, sharp, discrete spots like this, so then you consider that as a good single crystal. So if it is a good single crystal, you should see these kind of bright, round, sharp, discrete spots. Okay? So if you see something like this, okay, they are also okay. This is an average quality crystal, not a very good quality crystal. But if you find something like this, right, so then this is not a single crystal, that's a polycrystalline material. Okay, so then you can use fully automated structure solution. You can see here the single crystal, but if your crystal has to be like reasonably decent enough, good. Okay, so you cannot do for all the crystals. But I would always say preliminary scan I will do in automated mode, but later full data collection I will do manually. Okay, so it depends on your crystal. It can take from few minutes to few hours. Okay, so if your crystal is good, you will get your preliminary structure in few minutes. But if your crystal is bad, it can take few hours also. Okay, data collection can vary again from from maybe 30 minutes to 1 hour to 4 hours and 5 hours. Analysis can take another some time depending on your skill set. Okay, so how quickly you can do and how. Most of the time nowadays, most of them are automatic. You can do it. Okay, so you can see here, we just put the crystal, centered it, and then you see the goniometer has moved, and then you are starting the experiment. Okay, so let's see. It is just doing the preliminary scan. You can see the diffraction spot. They are discrete, bright, round, sharp spots throughout. It's rotating the crystal, taking the image, rotating the crystal, taking the image, rotating the crystal, taking the image. So it does a preliminary scan for 3 minutes, and then it tries to give you the structure. It's a preliminary structure, but then to make it 100% clear, you will invest another half an hour, 1 hour, depending on your crystals. It will give you structures. Okay, you can really purely depend on your crystal and then powerfulness of the X-ray source. So you have a very good powerful X-ray source. So you just have to utilize it with your crystals. Okay, you can see you have got the preliminary structure, and then it will continuously collects the data and process it, and then try to give you the final structure. So obviously, whatever the automation gives, so then authentication you have to do. Whether your chemistry is correct, whether it has put carbon in the carbon place, nitrogen in the nitrogen place, oxygen is in the oxygen place, you just have to double check. Okay, 90% of the time it does correct, but that 10% you have to evaluate, because X-ray will not be able to differentiate one electron. Okay, hydrogens cannot be determined by the X-ray diffraction, so it has to be done by the neutron diffraction. Okay, so that's why one electron difference always can be challenging. So make sure that your chemistry is correct, everything is correct, and then you can use this diffractometer to attain the three-dimensional structure of this. Okay, so then this is the yeah. Once you get the preliminary scan, so then there are some criteria for the data collection. Okay, you just cannot get preliminary scan and then okay, it's done. It's your proof, but you need to satisfy certain criteria. So what are those is, so you need to have a resolution of your data minimum up to 0.84 angstrom. Okay, and you need to have a completeness of your data which is around 98 and above 100%, and multiplicity should be greater than 3. So then you will tell who will check this whenever you make your structure. So to claim that is a correct structure, it has to pass the test called IUCR check SIF. Who is IUCR? It's an International Union of Crystallography. So they have set a exam. So your structure, your file needs to be updated. Which is the file? The file is CIF file, SIF file. People call SIF file, which is independent to your structure. Okay. What is SIF? Crystallographic information file. Okay. So that is independent to the per structure, and that structure has to go through this check SIF report, and then it should not have alert level A, which is a serious problem, alert level B, it's close to serious problem, alert level C, which is check and modify or clean, so then alert level G. Okay, so it should not have A and B at all. If it has A and B, you cannot publish the data because it is unreliable. Okay, so if it is C and G, it is okay. So that means if you have this much resolution, then you will not have an A level alert for resolution. Other things I cannot say, only for resolution. And completeness should be greater than 98%. Then you will not have an alert for the completeness. These are the primary things you should. So that's why when you are data collecting, so you need to set this criteria that I need to have a data which should be 100% complete, which should have a multiplicity 3, and which should have a resolution of 0.84. That means resolution is you are driving the goniometers. That means your diffractometer collects, but you should be able to see the diffraction spots as well. That's why your crystal has to be diffracting as well. Okay, so you simply cannot, I have put 60 seconds and then I am doing it. No, it doesn't work like that. You should see the diffraction spot, so then you can say. Okay, so these are the criteria for data collection. As I told you, it can take from few minutes to few hours. Okay, and this is a typical workflow of your single crystal. Like select the crystal and mount it, center your crystal to the X-ray, check the quality whether it is diffracting nicely, determine the unit cell. What is an unit cell? This is the smallest part of your crystal which repeat itself to go into three-dimensional structure. So we are not determining entire thing about crystal. We just diffract the crystal, we determine an unit cell, that's the smallest part. Okay, inside that unit cell, where are the atoms sitting? We are defining by the fractional coordinates, and based on that, how they are interacting, how they are packing, and so on and so forth, we are discussing. So that's the unit cell. Then collect the complete data, measure the HKL intensity data, correct and reduce, that means for the experimental correction, solve structure, refine structure, and interpret results. So I have put select crystal and mount and interpret in green, rest are all in blue. So that basically means the green part you need to take care, the rest everything will be done by the software and by the instrument. Okay, so the refining and interpreting the results is yours, and then putting the crystal is yours. Okay, so this is the applications in chemical crystallography, in protein crystallography. So you can use for any structure determination of small molecules, absolute configuration determination, solid state materials, metal organic frameworks, covalent organic frameworks, charge density studies, high pressure studies, high temperature studies, low temperature studies, protein, drug discovery, everything you can do with this instrument. Okay, detail you know already, I can skip these stuffs. Okay, and you can also do some advanced applications like very low temperature. You can go up to 28 Kelvin, but you need to have some additional setups for those stuffs, which is you can do some powder analysis, you can do some pair distribution function, so you can do some diffuse scattering, you can do some texture analysis, everything you can do provided you need to know how to do it. Okay, but the main purpose is the structure determination. So that's why I have given this slide as beyond routines. You are not doing these stuffs routines, but however you can do. So you can visit our Bruker website or YouTube. Just type what is single crystal X-ray diffraction. So it will tell you. It will lead to this video. You can also watch this video. So what is, just to summarize, that single crystal diffractometer is used for the structure determination, and it is not difficult method. It's a easy method, but you need to know a little bit about crystallography. But whatever you put the sample in, it may be depend on your data. So if your sample is good, data is good. Sample is bad, data is bad. Okay, so keep this in mind, and then that's the introduction I wanted to give you for today. Okay, so I can show you in the software just one data set, how we can process the data. Okay, so we have half an hour, right?
Just one quick question.
Yeah.